Hello, this is Mrs. Decker, and this is Objective 1B. I can use the mole ratio to convert moles of one substance to moles of another substance. Before we get started with today's lesson, we want to do a quick refresher of what the mole ratio is. So go ahead and pause this video and do the warm-up, and then come back for the answers. Alright, what is the mole ratio between aluminum and aluminum oxide? For aluminum, we have 4 moles, and for aluminum oxide, we have 2 moles. For the mole ratio between oxygen and aluminum, oxygen has 3 moles, and aluminum again has 4 moles. Okay, so now today we're going to learn how to use the mole ratio to convert between substances within a chemical reaction. So we're going to start with an example using s'mores to get an idea of what we're really trying to accomplish here. So I want you to write a balanced chemical equation for a s'more. So you need to think about what the reactants are for a s'more. So you would need 2 graham crackers plus 1 marshmallow plus 3 pieces of chocolate. And all together that will give you 1 s'more. So now that we have a balanced chemical equation for our s'more, we want to look at this problem. If you have 8 graham cracker pieces, 10 marshmallows, and 15 pieces of chocolate, how many whole s'mores could you make? With the graham cracker pieces, you could make 4 s'mores. With the marshmallows, you could make 10 s'mores. And with the chocolate pieces, you could make 5 s'mores. You can only make as many whole s'mores as your least amount of ingredients. So the total number of s'mores that we can make is 4. So the ingredient that limits the amount of s'mores you can make is the graham crackers. So now what we just did here is what we will be applying to chemical reactions over the next few lessons. I want to briefly go over the definition of what stoichiometry is so you have an understanding of what we're trying to do. Stoichiometry is the study of the relationship between the amount of reactants used and the products formed in a chemical reaction. Stoichiometry is based on the conservation of mass, and if you remember from our previous unit, conservation of mass says that mass is neither created nor destroyed. It is transferred from one form to another. In the case of a chemical reaction, it's transferred from the reactants to the products. So, because of the conservation of mass, the mass of the reactants needs to equal the mass of the products. Okay, so here we have a reaction of iron and oxygen to give us iron 3 oxide. So we want to take a look at what this reaction really means, what this equation tells us. It tells us that 4 moles of iron reacts with 3 moles of oxygen to produce 2 moles of iron 3 oxide. So the coefficients tell us the number of moles of each reactant and product. So we can calculate the mass of each of the reactants and the mass of the product to prove that mass is conserved. So if we have 4 moles of iron, remember to convert to mass, you're going to multiply by the molar mass of iron, which is 55.84. And that gives us a mass of 223 grams. And now take 3 moles of oxygen and convert that to mass by multiplying by the molar mass. And that gives us 96 grams. So if we add 223 plus 96, we get 319 grams of reactants. So now, if we take the 2 moles of Fe2O3 and convert that to mass, that also gives us 319 grams of product. So we have 319 grams of reactant, 319 grams of product. So we can see that mass is conserved. So now we want to look at all of the different parts of the reaction. So we're going to look at molecules, moles, and mass for each reactant and product. Okay. So the coefficients tell us the number of molecules. So there are 4 molecules of aluminum, 3 molecules of O2, and 2 molecules of Al2O3. The coefficients also tell us the number of moles. So there are 4 moles of aluminum, 3 moles of oxygen, and 2 moles of aluminum oxide. So we use the number of moles to find the mass. So for aluminum, we would multiply 4 times the molar mass, which is 26.98, plus the mass of oxygen, which is 3 times 31.98, and that gives us 204 grams for reactants. For the products, we multiply 2 moles times the molar mass of aluminum oxide, which is 101.93, and that gives us 204 grams of aluminum oxide. So if we look, the number of moles on the reactant side is 7 versus 2 moles on the product side. So number of moles is not conserved, but if we calculate the mass of each reactant and product, we see that mass is conserved between the reactants and products. Okay, so now we're going to look at an expanded version of mole island. You should already be familiar with mole island from Unit 4 within one substance. Okay, so we know we can convert between mass, volume, particles, and moles of one substance. Now we're going to add a second substance on the right side, and it's the mole ratio that helps us convert from moles of one substance to moles of another substance. So this is the step we're going to focus on right here, using the mole ratio to go from moles of substance A to moles of substance B. Okay, so example number 1 says how many moles of oxygen are needed to produce 12 moles of magnesium oxide. So 12 moles of magnesium oxide is our given information. Moles of oxygen is what we're looking for. So you want to start by writing your given information and draw your T-chart. So now we're going to use the mole ratio between magnesium oxide and oxygen to do this conversion. So again, remember when we look diagonally, we want our units to cancel out. So we're going to write 2 moles of magnesium oxide on the bottom, and we're looking for moles of oxygen, so we're going to write 1 mole of oxygen on the top. So now it's important to not only write your units, but your compound as well, because now we're converting between different compounds. So moles of magnesium oxide cancels out, and we're left with moles of oxygen, which is what we want. So you do 12 times 1 divided by 2, and that gives you 6 moles of oxygen. Example number 2 says how many moles of oxygen are produced by the decomposition of 6 moles of potassium chlorate. 6 moles of potassium chlorate is our given information, and moles of oxygen is what we're looking for. So write your given information. Okay. And then we're going to use the mole ratio to go from moles of potassium chlorate to moles of oxygen. So on the bottom, we want to write the moles of potassium chlorate, which is 2. And on the top, we're going to write 3 moles of oxygen. Okay. Now, this problem has nothing to do with KCl, so we're not going to use that anywhere in our problem. So to solve the problem, we do 6 times 3 divided by 2, which gives us 9 moles of oxygen. And our last example problem says how many moles of hydrogen are produced from the reaction of 3 moles of zinc. So 3 moles of zinc is our given information. Moles of hydrogen is what we're looking for. So start by writing your given information and your T-chart. And we need to put moles of zinc on the bottom there's 1 mole of zinc, and moles of hydrogen on the bottom, and there's 1 mole of hydrogen. So we're left with 3 moles of zinc. Now, it's likely that your answers as we get further into this will not be whole numbers. For simplicity's sake, we're starting off with whole numbers, but moles will often be a decimal. You have practice problems on the next page of your packet. Go ahead and work on those and let me know if you need help.